Ever stop to think that without that amazing highway of nerves running down your back, your brain would basically be a GPS with no car to drive?
Hmm. Interesting way to put it.
Today, we're taking a deep dive into that often overlooked superhighway, your spinal cord.
It's more complex than just a cord, despite the name.
We've got a section from the medical textbook, Spinal Cord and Spinal Nerves, ready to break down just how this whole system works. So before we get into the nitty-gritty, set the scene for us. How big are we talking? Where does it live? That kind of thing.
Picture this. A roughly 16 to 18-inch cable running down the center of your spine, starting at the base of your brain and exiting through an opening called the foramen magnum.
So it's like the ultimate protected cable running through the bones of the spine itself.
Exactly. But here's where it gets really interesting. It doesn't actually run the full length of your spine. It stops around the L1 vertebra, which is in your lower back.
Wait a minute, so what happens below that? Do our legs just run on autopilot?
Not quite. From that point downward, instead of a solid cord, you've got this bundle of nerve roots fanning out almost like a horse's tail.
A horse's tail made of nerves. Medicine has to have a more elegant term for that.
It's called the cauda equina, which is literally Latin for horse's tail. And this arrangement is actually crucial for our flexibility. Imagine if we had a thick cord running all the way down. Bending over would be quite a challenge.
That makes so much more sense. But if the spinal cord isn't as long as our spine, why do we even have all those extra vertebrae?
It all comes down to different growth rates. Our vertebrae keep growing for longer than the spinal cord itself during development, which is why they don't line up perfectly one-to-one. And speaking of those vertebrae, the spinal cord is divided into segments that roughly correspond to the different sections of your spine: cervical, thoracic, lumbar, sacral, and coccygeal.
Ooh, that's a mouthful. Is it really important to memorize all those names?
While you don't need to be reciting them in your sleep, understanding these segments is clinically helpful. They tell us where specific spinal nerves branch out and which parts of the body they control. For instance, the cervical region, which is up in your neck, houses the nerves responsible for your arms and upper body. Interestingly, this region of the spinal cord has more gray matter compared to other sections.
More gray matter, meaning more processing power. Is that because our arms are doing such intricate work all the time?
Precisely. The source emphasizes that the increased gray matter in the cervical region provides the extra neuronal density needed for the fine motor skills of our hands and arms. And it's not just the cervical region. There's a similar enlargement in the lumbosacral region to handle the demands of our legs and feet.
So our spinal cord has its own version of rush hour traffic, just like a real highway. This delicate system must be seriously well protected. What's stopping it from getting jostled around every time we move?
That's where the meninges come in. They're layers of protective membranes that surround the spinal cord just like they do with the brain.
Meninges, those are the layers everyone forgets about unless something goes wrong, right?
Hmm.
What's the source say about how these actually protect our spinal cord?
Well, they're a lot like those high-tech phone cases you see, but for your spinal cord. The outermost layer, the duramater, is tough and fibrous, like a hard shell. That's your first line of defense.
So if the duramater is the tough outer shell, what's underneath?
Next comes the arachnoid mater, which is named for its web-like appearance. It has these delicate thread-like strands that create a space filled with cerebrospinal fluid, kind of like a built-in shock absorber.
Cerebrospinal fluid, that's the stuff they check with the spinal tap, right?
Exactly. It's like the spinal cord's own personal jacuzzi, cushioning it from shocks and bumps. And finally, you have the pia mater, the innermost layer, which is thin and delicate, clinging directly to the surface of the spinal cord. It's rich with blood vessels, providing nourishment to this vital pathway.
Wow, those are some serious layers of protection. It's like the spinal cord is traveling first class. But let's talk about the content of this information superhighway. What's the source say about the different lanes of traffic inside the cord itself?
Think of it this way. You have your local roads and your expressways. In the spinal cord, the local roads are represented by the gray matter, which forms that distinctive butterfly shape you might have seen in diagrams. That's where the neuron cell bodies, the command centers, reside, along with dendrites that receive signals.
And the express lanes, those must be important for those split-second reactions.
Absolutely, that's where the white matter comes in. It surrounds the gray matter and contains the myelinated axons, those long insulated fibers that allow for rapid signal transmission. It's like the fiber optic cables of the nervous system.
So it's all about speed and efficiency in the white matter.
Exactly. And this white matter is organized into distinct columns called funiculi. You've got the posterior, lateral, and anterior funiculi, each carrying a mix of sensory information heading up to the brain and motor commands coming down from the brain.
A two-way communication superhighway. Now I'm picturing all these signals needing to get on and off the highway. That's where the spinal nerves come in, right? Those exits and entrances connecting the central nervous system to the rest of the body.
You've got it. We have 31 pairs of these spinal nerves, each branching out from the spinal cord at different levels. And here's a key point from the source. These are mixed nerves, meaning they carry both sensory information coming in from the body and motor commands going out to the muscles and glands.
Okay, so it's like those highways that have traffic flowing in both directions. What determines which spinal nerve controls which part of the body? Like if I wiggle my toes, how does that signal know which off-ramp to take?
That's where the concept of dermatomes comes in. Imagine your skin is divided into distinct zones, each supplied by a specific spinal nerve. That's your dermatome map. So if you feel a sensation on a particular patch of skin, doctors can trace it back to a specific spinal nerve.
So it's like a diagnostic roadmap for the nervous system that's really useful clinically.
It is. The source mentions it's particularly helpful in pinpointing the location of a spinal cord injury or nerve damage. And here's another fascinating thing about dermatomes. They're also involved in something called referred pain.
Referred pain. Is that when you stub your toe and your whole leg hurts?
That's a good way to think about it. But it can be even more bizarre. Referred pain is when pain originating from an internal organ, like your heart, is felt in a completely different part of the body, often on the surface. For example, someone having a heart attack might feel pain in their left arm or jaw.
Wait, so my brain could be getting its signals crossed. That sounds kind of unnerving, like my body's playing tricks on me.
It's because the brain sometimes struggles to interpret pain signals from internal organs. It's like it's saying, well, this signal's coming from the same area as my arm, so maybe that's where the pain is. Fascinating, isn't it?
It really makes you appreciate how complex this system is. So we've covered the individual spinal nerves, but the source also mentions these things called nerve plexuses.
Plexuses are where things get really interesting. Imagine several spinal nerves coming together and braiding their fibers. That's essentially what forms a plexus.
Braiding nerves, that sounds messy.
It might sound chaotic, but it's actually a brilliant design strategy. By intermingling fibers from multiple spinal nerves, these plexuses create redundancy. So if one nerve gets damaged, it doesn't necessarily mean a complete loss of function in that area.
So it's like having a backup generator or a detour route in case of a roadblock.
Precisely. The textbook highlights several key plexuses, each controlling a different region of the body. We have the cervical plexus, the brachial plexus, the lumbar plexus, and the sacral plexus.
Okay, that's a lot of plexuses. Give us the rundown. Where are these located and what do they do?
Starting at the top, we have the cervical plexus, which is up in your neck, controlling muscles and sensation in your head, neck, and shoulders.
And that's where the phrenic nerve comes from, right? The one responsible for breathing.
You got it. It's a great example of how the spinal cord and its nerves aren't just about movement. They're also essential for vital functions like breathing. Then you have the brachial plexus, which originates from the lower cervical and upper thoracic segments.
Brachial plexus. I've heard athletes talk about injuring that one.
It's a common site of injury, especially in contact sports, because it controls all the movement and sensation in your shoulders, arms, wrists, and hands. Damage to the brachial plexus can cause weakness, numbness, or even paralysis, depending on the severity.
Ouch. Okay, that makes those stingers in football games even scarier. What about the other two, the lumbar and sacral plexuses?
Those are farther down, controlling the lower body. The lumbar plexus innervates muscles in your abdomen, hips, thighs, and even plays a role in knee extension.
And if I'm not mistaken, the sacral plexus is where that big one, the sciatic nerve, branches off from.
You're right on the mark. The sacral plexus, located in your lower back, is responsible for the back of your thighs, legs, and feet. It's the largest nerve in your body, and when it gets irritated or compressed, it can cause that shooting pain down the back of your leg known as sciatica.
Sciatica, definitely not something I want to experience. This whole conversation makes me realize we take our spinal cords for granted until something goes wrong.
It's true. We often don't appreciate this incredible network until it's not working as it should. But there's one more amazing function of the spinal cord we haven't even touched on yet. Reflexes.
Reflexes, those are the things that make you accidentally kick the doctor when they tap your knee, right?
Yeah, that's one example.
Yeah.
But on a more serious note, reflexes are those lightning-fast actions your body takes even before your brain has time to fully process what's going on. They're the spinal cord's way of saying, I'll handle this, in those crucial milliseconds. That could mean the difference between a near miss and an injury.
So it's like having a built-in emergency response team ready to act at a moment's notice. What does the source say about how this actually works?
Think of it as a five-step communication relay, with the spinal cord acting as the central hub.
Yeah.
It all starts with a stimulus, so you touch a hot stove. That heat activates sensory receptors in your skin, and that's step one.
Okay, so we've got a signal. What happens next? Does it go straight to the brain?
Not so fast. That's where things get really interesting. Instead of taking the scenic route to the brain, the signal takes a shortcut. Step two is the sensory neuron carrying that ouch hot message directly to the spinal cord.
The spinal cord is where those interneurons come into play, right? Like the dispatchers deciding how to respond to the emergency.
Exactly. Step three, the interneurons in the spinal cord analyze that incoming sensory information. They're the ones deciding how best to respond, and sometimes that decision is made without even bothering the brain. These super fast reflexes, like the knee jerk we talked about, are called monosynaptic reflexes.
Monosynaptic reflexes, so it's a single connection, a direct line from sensation to action. That explains why they're so fast.
Precisely. But not all reflexes are quite that simple. Sometimes the interneurons recruit other interneurons, creating a more complex relay system. These are called polysynaptic reflexes. Poly, meaning many, and they involve a bit more processing.
So is that what's happening when you touch something hot and it takes a moment for your hand to actually pull away? It's not instantaneous, but it's still pretty darn fast.
Exactly. The withdrawal reflex is a classic example of a polysynaptic reflex. Those extra connections add milliseconds to the response time, but they also allow for more nuanced reactions.
Okay, so we've got the sensory input, the interneuron action. What are the final steps in this reflex arc?
Step four is all about sending out the response team. Once the interneurons have made their decision, a motor neuron carries those instructions out of the spinal cord and towards the target muscle or gland.
So it's like, all right, team, here's the plan. Execute.
Exactly. And that brings us to the grand finale, step five, the effector response. This is where the muscle or gland swings into action, carrying out the instructions from the spinal cord. In the case of that hot stove, your arm muscles contract, pulling your hand away from danger.
And all of that happens in the blink of an eye thanks to the incredible power of the spinal cord. I'm starting to think we don't give this part of our nervous system nearly enough credit.
I completely agree. This deep dive has only scratched the surface of what the spinal cord does for us every second of every day. It's involved in everything from the simplest reflexes to complex movements, from regulating organ function to relaying sensory information.
It really makes you realize how interconnected our bodies are and how vital the spinal cord is to our ability to move, feel, and interact with the world around us. Any final thoughts for our listeners to ponder as they go about their day, newly aware of this incredible superhighway running down their backs?
Next time you feel a gentle breeze on your skin, or catch yourself before tripping over a curb, take a moment to appreciate the intricate network of nerves and signals that made that sensation or reaction possible. It's a marvel of biological engineering, and we've only just begun to unravel its mysteries.
Beautifully said. Thanks for joining us on this deep dive into the often overlooked but always essential world of the spinal cord. Until next time, keep those brains engaged and those spines flexible.